What's up, my peoples? Yeah, I'm back after a very long break because I had a lot of finals and it's finally summer, so hopefully I'll be getting back on this physics stuff. Anyway, yeah, we're doing problem 3.5 in Everest. Um, yeah, it's a F-equals problem, which is a real problem. So this will be useful. So you guys should try this yourself first. Then yeah, I'll give my solution, which is actually a little bit different from the book. I was reading the book and I was like, wait, this solution is pretty confusing in my opinion. So yeah, this is a solution that's not in the book, and it's like my perspective of things, which I think is a bit more beginner friendly because I feel like I'm still a beginner sometimes. But yeah, let's get started. So a block of mass M is attached to a massless string. The string is passed over a massless pulley, and the end of the string is fixed in place. The horizontal part of the string has a length L. Now, a small mass is hung from the horizontal part of the string, and the system comes to equilibrium. Neglecting friction everywhere, the tension at the end of the string is blank, and during the process, the block has been raised by approximately a height of blank. Okay, so let's do this. So let's do part A. And part A is asking about the tension. The tension. Um, so here's our diagram. So here we can obviously see that the tension is mg. And the reasoning behind this is if if the tension in one part of the string is mg, the tension in every single other part of the string must also be mg, right? They have to be the same. In a massless string, in a pulley system, or yeah, maybe just in general, in a massless string, right? The tension has to be the same everywhere in every segment. Because if it was different, then the net force would be different, and then it would start accelerating. So yeah, here's mg. Now you have the second diagram, and this is where like the trick gets a lot of people. People are like, oh, if you add another block, the tension will be greater. But it's actually just the same logic here. If the tension here is mg, it has to be mg everywhere else in the segment. There's no other exception. So yeah, therefore the answer is B. Okay, that's good. Now we're gonna move on to part B. And this is where the solution I was talking about was getting a little bit confusing. The Everest book is pretty confusing. I think like some of the solutions are really poor written. That's actually why I started this YouTube channel. I also started this YouTube channel to have some fun. So yeah, let's do this. So the during the process, the block has been raised by approximately a height of blank. Okay. So this is where a really nice trick that I think I've talked about before comes in. And basically the trick is to use different like scenarios, different like frames of reference, not like frames of reference in this situation. We'll get to a problem where it's like frames of reference, but different situations and you can get different equations from. So like that's like a lot of yaps. So yeah, I'll just show you how to do that. So first we have this situation, right? And I know the problem is saying the horizontal part is L. I don't care. I don't care about the problem. I'm going to do whatever I want. Okay. So let's say this is D because I want capital L to be something else. Let's say this is D and this segment is going to be Y initial. Therefore, the total length of the total length of the string has to be D plus Y, and total length is capital L because usually it's capital when it's like the total of something. Okay, and the reason this is actually like a thing. This is a real thing. It's called conservation of string. Basically, how you traditionally see it is like in like vertical pulleys. So like this, and you could say like, oh, this is S1, this is SI, S2. So the total length equals to S2 plus SI. We can also like apply to horizontal part as well, which is pretty neat. And I don't think they discuss problems like that, unless they do. Not sure. Anyway, yeah. So adding up the segments of the string gives you the total length of the string, which is pretty obvious. Adding up the segments of the string gives you the length of the total string. Okay. This is the conservation of string. So let's move on to the next one. And this is where we get another interesting equation. So yeah, here it is. So basically, I want to do the same thing. This is D again. This is D again, and this is gonna be Y final. So we're gonna have to add up the individual segments of the strings, which means we need to find this segment and this segment. So yeah, let's do that. So I'm just gonna break it into a triangle, and I'm gonna take this triangle here. We don't know this yet, but we'll figure this out. This is theta, and this is D over 2, right? Because if you put the mass in the middle, I think it's pretty intuitive that right, if I have a mass here, right, I think it's pretty intuitive that the mass wouldn't stop here. It would stop in the middle because the derivative it equals 0 here. It's like the lowest point of energy. It always sells in the lowest point of energy. I think it's pretty self-explanatory that's d over 2. Okay. So this length is d over 2, and we want to find this individual segment. So this is the adjacent side and this is the hypotenuse, meaning that we must use cosine theta equals to d over 2 all over the length that we want to find. So the length that we want to find equals d over 2 cosine theta. Okay, so now we found one segment. We want to find the other segment. And luckily for us, the other segment is going to be the same. Actually, yeah. So we're just going to multiply, and we're going to get the L. I'm going to call this, well, we multiply by both sides, right? So you got 2L. I'm going to say 2L is going to be LH, and H means horizontal. And it's going to be D all over cosine theta. This is LH. Now we have this D all over cosine theta. Now we have to add our y final in order to get the total length. So this is what I mean, right? We have two different like equations using two different scenarios, and we're using this conservation law and we're abusing it. Yeah. Yeah, they don't really discuss this solution. I think they jump to like a really I don't know how they do it, but they like start jumping and stuff like that in the solutions, which is pretty annoying. But yeah, so now you can see I got this equation, right? And now next we need to find theta. So theta is how do we find theta? So theta is gonna be like this. Uh theta, right? So mg and we have theta. So here we have two tensions. We have two tension forces holding this block up, right? And it's going to have components in the x direction and the y direction. And we won't only want to focus on the y direction because we have this force vector pointing down. And before anyone says, "Hey, you forgot this block," I didn't. You can ignore it, I think, um, because you're gonna need to account for the tension here as well, and and the block here. So you just do the sum of the forces, and actually works out perfectly fine, I think, because physics, as long as your physics is right, it will work out perfectly fine. I think that's pretty self-explanatory, actually. I don't know, what am I even saying? Okay, I'm gonna get like a midlife crisis at the age of like 16 or something like that. I'm not even 16. Okay, anyway. Um, yeah. So so let's solve for the theta. Yeah. How do we do that? So we know this part is gonna be t sine theta because trigonometry. And then if this part is t sine theta, what is t? And this is where the first question actually comes in. And t equals mg sine theta. Yeah. So here we get 2mg sine theta equals to mg. Now we cancel on both sides, and when we divide, we get 1 over 2 equals to sine theta. And this is summing theta equals 30. You can use a calculator, but I just memorized that this is the right answer usually. I think because this like th sine theta equals 1/2. It comes up so much in physics. So yeah, I just memorized it. So yeah, theta equals 30. So now I have d all over cosine 30 plus yf equals to L. But what else does L also equal to? L is also equal to D plus Y initial. Okay, so D plus Y initial. And what are we solving for overall? We're solving for the change in the height. What is the change in the height? When we solve for the change in the height, we want YF minus Y initial. This is going to be the variable we want to solve for. And we get D minus D all over cosine 30. So if let's just write this as a different notation. If we factor the D out, we get 1 minus 1 all over cosine 30. And we are very close to the answer. Too bad I don't have Desmos. I'm going to load that up real quick. All right, so I just loaded Desmos, and yeah, let's just do this. So we get negative 0.5, and let's take that. Let's go to Excel. This is, yeah. So you might be wondering, why is the answer negative? Why is the answer negative? 1, 5D. Okay, and the answer, if you think about it in perspective, right? Let's say this is YF, and this is Y initial. Why, if you subtract these, you're going to get a negative length. And that's why I got a negative length here. So, yeah, I think I low-key messed it up. I think it should be an initial minus final, which is a change. But anyway, we got this number, and it doesn't really matter because you can just inference that it's this. Yeah, that's the answer. That was the change. That was change. I think it was how much did it go up by? Yeah, yeah. So I should have done initial minus final because if you look at the initial is obviously going to be longer, right? So I should have this is length is 0.15D. Okay. Yeah, if you have any questions on that, because I know like the explanation was that good, yeah, just you can type a comment. But yeah, we got this question done, which is pretty good. This is a tricky one. So yeah, thanks for watching. I'll see you. I'm not sure when I'll record my next video, but I'll see you guys another day. Yeah.